Hello, everyone. Welcome to this short recording related to our last lecture in machine learning course about clustering algorithms. It was presented in the lecture that we wrote a code for k-means clustering, and also we introduced, or we explained in the lecture about expectation maximization algorithms. I received email from one student that he wanted me to write a simple code in the same way that we did in the k-means coding in Octave, or of course Matlab. It should work with both algorithms. As I mentioned in the lecture, those codes not for application purpose, but just for explanation. So of course they are working very well, but for the explanation of the algorithm in the course. So it is not optimized to use, for example, minimum time and minimum memory and so on. So we didn't optimize in any means the resources of the computing. But we explained just how the concept, how the expectation maximization clustering algorithm works. So this is the purpose of this code. So I wrote this code. I will put it in model. So the idea of this code and the purpose actually of this short recording, just to show you how to use the code. It is in the same way that I recorded some recording how to use artificial neural network code that I wrote for this course, and also the k-means code, which was also written for the purpose of the explaining the algorithm. So this code is a simple function. So you can see that in front view that we have this function. I call it EM, expectation maximization cluster, and you put A. A is matrix with the entries, and that you want to cluster. You don't have any label. Remember, we don't have labels here. We have just data, and this data, it has dimension D, and it has the number of entries n. So the size is n by d, as you can see. So it is n by d. So you have n rows and d column. The number of columns are the dimension of data. N is the number of entries. Okay, and k is the required number of clusters. So you guess how many clusters in this data, and you want to cluster them to k different clusters. Okay, and you can see here the function will return to you PMCWF. What they mean, B is the probability of each cluster. So it is a priori probability. So for example, each cluster, what is the probability of each cluster? Like 30%, 40%, 80%. It depends on the number of clusters, and it depends on the data which has been assigned, the average assigned to this cluster. Remember that we use here soft assignment. So we don't have hard assignment for data. So for example, this entry can be, let's say, 90% assigned to this cluster and 10% assigned to another cluster, as I explained in the lecture. We have also M. It returns to you the mean vector of each cluster. So for example, if you have the dimension of each of the data is 5, and you have 3 clusters, so in this case M will be 3 rows and 5D, 5 columns. Okay, it gives you the mean of each cluster, the mean vector of each cluster. C gives you the covariance of each cluster. So it will be like cell contains the covariance of each cluster. Okay, WF finally is each entry data. It is like a probability to be assigned with each cluster for each entry of the data. So this it return to you the soft probability, of course, of this data. So the code, as I said, it is very simple, very straightforward. What I did here, I put the function for the likelihood function to be like multivariate normal distribution. It can be, of course, any distribution that you can add here. So you can test different kind of distributions. okay, and it will be repeated this code until we got the probability of changing the primary probability of changing of each class to be less than 0.001. You can of course change all these values as you like. Okay, and how it works. So I also run another code, or I wrote another code to run this expectation maximization clustering algorithm. So this function will run this EM algorithm in a simple case. In the beginning, I clear everything, and then for the purpose of testing of the algorithm, I defined the data which has dimension of 5. So the dimension means that it has 5 columns, okay? And then I define the first cluster. Of course, now I am testing. I am testing the algorithm. So I need to define the clusters and define the covariance of each cluster. And then I try to find if my algorithm is able to catch these hidden clusters and deviate between them and differentiate between them or not. Okay, so in this case, I define the mean of cluster 1. It is 0, 1, minus 1, 5, 0. And the covariance of cluster 1, it is, I just generate a random number 5 by 5, but we know that the covariance should be symmetric matrix. So I multiplied it covariance by covariance transpose. So I have now symmetric matrix. It is a random matrix, okay? And then I define the cluster 2. In cluster 2, I define different mean than the cluster 1. And also I define the covariance of the cluster 2. And in this case, the covariance was random, not normal distribution, but with random distribution. So I just use another distribution, and then I also multiply it with the transpose. So we have the second covariance matrix, and then the third cluster, it has this mean, which is also different than the previous means, and also I generate different random like class covariance matrix, and then I multiplied it also with the transpose. So we have different covariance matrix for each cluster. Okay, now I generate the numbers. So for x1, it will generate 100 entry with the mean mu1 and with the covariance co1. Okay, so this I use this function. It is a multivariant random normal random distribution. It is built-in function that you can use in Matlab and also in Octave. So you can use this code run both in this programming language without any changes. Okay, and then I generate also x2, and in x2 I used different number of entries. So I use only 80. I want to use different number of entries in each cluster, so not necessarily to be in the same number. And then I use mu2 and covariance 2, and also for x3 I use also 120 entry with mu3 and covariance matrix 3. Finally, I arrange all matrix or all these numbers within one matrix. So now X matrix contains X1, which is 100 element, 5 column. Under it, there is matrix 2, which is 80 rows and also 5 dimensions. And finally, the third matrix, which is 120 column, sorry, 120 rows and also 5 columns again. So totally we have 300 rows and 5 columns. This is your data. To make things more natural, not necessarily that every cluster to be within each other. So it can be like randomly merged. Okay, because of that, I use this function. So I generate matrix A, which is the same X, but now I use random like random shuffling of the data. So not necessarily to be the whole column 1 together, the home cluster or the whole cluster 1 together and the cluster 2 together. No, now they are randomly like shuffled within the matrix A, as you can see. Okay, now I want to test my code. This is my code now. Okay, here the number of, I assume that I know the number of clusters. I will change the number of clusters and we will see how this will affect the clustering process. And then I just run my code. So you can see here in my code, I have A. A is the matrix with 300 elements, okay, and 5 dimensions. And I asked it to say that I have three clusters. Okay, and I don't have any label. I didn't mention that this entry belongs to that label. I want this cluster to find by itself how to cluster every cluster together. Okay, so I will just run this code. As you can see it, I will run it. Okay, now it is done. Okay, now let me see how the probability was distributed for each cluster. If you just show what is B. So B now gives you the clusters. For first cluster, it has probability 0.3885. The second cluster has probability 0.2667. The third cluster has probability 0.3448. Remember that the sequence of clusters not necessarily to be the same sequence I gave here. So those are supposed to be random numbers. So we don't know anything about the generated data. Okay, but anyhow, those gives you the probability of each cluster. Okay, now let me see what is the probability of the original clusters here. So in my generated data for this cluster, I have 100 out of 300. So it means that 100 divided by 300, so the probability is 0.33. So most likely the third cluster here in this data representing the first cluster here in my generated data. Okay, now the third one is 80. So in 80 case, so we have 80 divided by 300. So the probability should be 0.2667. It gives 0.6. It gives it exactly the same. Actually, it is amazing. It gives the exact. Most likely, it has grouped all data from this cluster correctly. And finally, the third cluster should be 120, which means that the probability of priori probability of this data should be 120 divided by 300 data should be 0.4, which now it gives 0.3885, quite close. Okay, now let us see the mean. What will be the mean of each cluster? As I said, we have 3 clusters, then I have 3 means. Okay, let me, because I generated the data myself, so I know the mean. The mean of the first cluster, this one, the mean of the second cluster, this one, and the mean of the third cluster, this one. So now I can check the mean, M. So the mean gives you, as I said that for the first cluster, it seems that the first probability is for the third cluster in my generated data. So the first one here, it gives you 0.2269, 1.47, minus 0.9, 5.2, and 0.46. Okay, let me check the mean of the third cluster. So you can see this is the mean of the first cluster. Okay, for the third cluster. So here the original data is 0. Now it is 0.2. This one is 1. Here is 1.4. This one is minus 1. It gives us here minus 0.9, quite very close. Here is 5. Here is 5.2. Here is 0. Here it gives 0.42. For the second cluster, which should be the same, the second here, what we generated, here the mu is 2. The calculated mu in my code is 2.19, 0 is 0.19, 1 is 1.06, minus 2 is minus 1.8, 3 is 3.13. Actually, amazing. It is very, very close to the original data. And finally, for the third one, it is 0, 1, minus 150. It gives you, for 0, it gives minus 0.19. For 1, it gives 1.13. Minus 1, it gives minus 1. And 5, it is 4.8. And 0 is 0.09. So it is actually amazingly working in very nice way, very nice way. So remember, no labels. Just you throw this data, just raw data without any labeling, and this code was able to cluster them correctly, amazingly correctly actually, because now the data is finite. Maybe you can ask why here is, for example, 2.19 and it should be 2. Because remember that the number of data is finite, is 80 and 120 and 100. So it uses likelihood, maximum likelihood to find this mean and covariance. Which with finite data, we expect that we always will have some error. Of course, if the data is more, then we will have less error. Now you can also check the covariance. If you want to check the covariance of each data, let me take the second one. So the covariance matrix for the second one, it is here it is C capital, so I will put here C, and I want to see the covariance of the second data. Okay, in after the expectation maximization algorithm. Okay, so why I use squeeze here? Because for the covariance I use cell, not matrix. It is cells, because I have k number of cluster, and in each cluster I have two-dimensional covariance. So I use cells instead of using matrix. So now this will be the covariance matrix, as you can see. I can compare it with the covariance matrix that I generated in the second element, which is CO2. So if I wrote here CO2, so then we can compare both covariance. So here you can see the first element is 2.825, here is 2.7. And if I take some other elements, so if I take here 1.599, here it will be 1.58. And here is 1.72, here is 1.76, here is 1.19, here is 1.3. So actually they are like close in quite proper way. Okay, what happens if I repeat the data? Of course, if you repeat the run, you will get a new result, because you will generate a new random of the covariance. Then you will have random signals, or you have random or different results in this case. But every time it will be very close to the original data that you have. Okay, if you want me to repeat it, I can repeat the run again. So now you can see, let us look to the mean, for example. It is enough to the mean. So now you can see the new mean. So it is 0.1 in the first element, 0.9, 1 minus 0.2, which one is close to this number, where the third number is minus 1.2. It should be this one actually. Mu1 is the same, so it is, here is 0 is 0.1, 1 is 0.92, minus 1 is minus 1.22, and 5 is 4.8, and 0 is minus 0.2, and so on. So it works actually in very nice way. Now, assume that you don't know the number of clusters. Okay, if we have two clusters, for example, then I would put k equal to 2 and let me run. So when you run the code, now it will classify the data into two clusters. Okay, so in two clusters, then you can see this is a cluster 1 and a cluster 2. It will merge those which are very close to each cluster to be within each with the data to be within their cluster with certain probability. Of course, it happened with certain probability, which we can find with WF. So if you can look to the WF, you can see the probability of each element. You have 300 elements here. For example, in this element, it was hardly assigned to cluster 2 and 0 for cluster 1, but not necessarily that every data that you have. For the data which are close to the border between elements, you might have different clustering. Like this one is 0.99, 0.01, and so on. But okay, let me check what happened if I cluster this to more than the number of real clusters. So if I put 4 clusters, the original one was 3 clusters. Now what happened if I put it to 4 clusters? Okay, so after generating this, and now I want to see the probability of each element. So you can see here, because for example, in this entry, it was 82% to cluster 1 0.17% to cluster 2, and it has been now reached to be 0 in cluster 3 and 0 in cluster 4. It was very like far away from clusters 3 and 4, but close on the border or close to the border between cluster 1 and 2. And you can find different clustering algorithms or numbers between clusters. Of course, I repeat here the number of iterations many times until they will assign it to each cluster. And in this case also you can find the mean of each cluster, the covariance of each cluster, so you can put the number of clusters as you want. Sometimes when you put the number of clusters too much, then sometimes some clusters can be empty. And when some cluster is empty, this code might generate error. So not generating error, it will work, but you will get some non-number result for some clusters. Of course, this problem could be solved easily by adjusting the code. I will put the code and also the run of this code in the model so you can use them. And you can also study how the code is working. So usually if you want to check that if you understand some algorithm or not, if you can code it, it means that you understood it very well. If you cannot code it, that means that there's some gaps in your knowledge about this algorithm. So you need to study more until you'll be able to code it. Okay, again, this code it works fine, at least based on my testing, but I cannot guarantee that it will work for every situation or for every kind of data. And also, I am sure that for the expectation maximization clustering, there are much more like sophisticated and optimized codes in Python or Julia or Matlab. Thank you very much. And if you have any questions about the code, you can write your comments in the model page. Thanks, and see you in the next recording. Bye.